All right, 216. So I was making a very bad mistake while calculating pressure forces because of my differential, right? I was doing a mistake that's not easily caught while uh, yeah, checking what's going on. So you can't figure out whether or not you're making that mistake right away. But yeah, the mistake was that the differential element that I took, right? So this was how it yeah, so right, you got this spherical shell, a very thin spherical shell, and you're taking a solid angle out of that. So this is how the thing is looking. So it's kind of like a box, but not really. And then this surface is actually having some kind of curvature, right? Yeah, that was the element that I took. So the problem with this thing is what I thought was, okay, there's pressure over here and pressure over here. The difference of these pressures, that times the area, or actually not like that. I want this pressure times this area and then this pressure times that area, right? So these forces, the difference of those forces, you get the net force, right? But I didn't take these sides into account. So you might think, okay, I mean, like these sides, they will have forces pointing in this direction and in this direction and so on, right? So they don't contribute to the radial force, but then they do, unfortunately, because right, it's not actually a cubical volume. Instead, it's actually having, how do I say this thing? So this area is actually smaller than this area, and because of that, what's actually happening is that it looks something like this. This is how the volume should actually look. So yeah, okay, this is how it should look. So if I drew it like that, then it would look like this. I know that over here this angle is unreasonably big, but you get the idea that there is a bit of a bit of a slope over there, right? So it's not zero, and because of that slope, you get this extra area where your pressure actually acts, and this area is in fact the same thing as this area, right? So yeah, I know it sounds weird to actually imagine this thing, but trust me, this area is actually the same thing as this area. So whenever you take the projection of this area along the plane perpendicular to r vector, right, you will get this area. So the sum of these areas, that's actually the same thing as this area. So really what we have to do is this area times the pressure difference. That's the force that we should be looking for. So what would that area be? I mean, it's approximately just sigma. I know it's actually supposed to be only the area which is perpendicular to r vector, right? So it should not have the actual area that we will calculate is this area. But then come on, those two are almost the same. You don't have to worry about that all that much. So really, and if you are still worried whether or not this is correct, go watch my other video where I took almost something like this. So something that has similar stuff going on, except that it's much more symmetric and easily doable, right? So check out that video. Uh, right. I don't know what was this name. Yeah, its name was the most inefficient way of calculating gravitational pressure. So I, yeah, basically made that whole note after I did this 216th question. And right, and now let's do it the correct way. So you just got the solid angle, whatever the solid angle might be, times r squared, that is this area, right? Or you know what? Yeah, scrap that. We'll just say A. So, or dA. Does that even matter? dA, that's the area. So this thing times dr, that is the whole volume. That times the density, that's our mass. Then you got G capital M, which is G times 4/3 pi r squared, sorry, pi r cubed times density, that's the volume. Oh, sorry, that's the mass. Okay, times this mass, right? This thing upon r squared, that's the gravitational force, and that's equal to the change in pressure. So like dp, actually it should be negative because it's supposed to be, right, the force is supposed to oppose our gravity force, and because of that dp must be a negative quantity. As your radius changes, your radius increases, your pressure should decrease. So it's really just negative dp times this area, so dA, right? So this element That makes sense. That's just that force. So this cancels out. Isn't that awesome? And we just get this thing. Some other stuff will cancel out. So just get, yeah, R over there. And what is this? It's 4/3 G pi rho square because two rows are there, and then you got R T R. Yeah, everything is in there. And that is equal to negative dp. And then just integrate this thing and assume that the atmospheric pressure is 0, because otherwise, how do you do this thing? Um, Actually, no, we should assume that the atmospheric pressure is not 0. We'll just say it's P naught, right? Yeah, because we want realistic assumptions. So it is right, correct to assume that it's P naught, not 0. And what we want is P as a function of R. So at some R, what is the P going to be, right? So your integration, it's going from the surface to the point. So it's like, or okay, let's do the opposite. So from this point to the surface. So then integration of negative dp, it is going to be negative of, so yeah, like P naught minus P basically. So that's basically P minus P naught. Yeah, this quantity, and that is equal to, so you got a half and stuff, you got 2/3 G pi rho square, and then R square upon 2 delta R square. The upon 2 is already gone, just delta R square. So it's going from this to that. So it's like capital R square minus small r square. Make sense? Cool. And that also makes sense because the pressure P actually is bigger than P naught. So there we go. So P is just equal to P naught minus 2/3 G pi rho square R square minus R squared. Interesting, isn't it? Yeah. All right, once that's done, this will be the next question. So 217th. Find the proper potential energy of gravitational interaction of matter forming a thin uniform spherical layer of mass m and radius r. So potential energy of gravitational interaction, okay, of matter, fine. What do you mean by proper potential energy? You mean total potential. So the self energy plus the, yeah, you get the thing. So thin uniform spherical layer of mass m and radius r. Okay, you want to form that first. And a uniform sphere of mass m and radius r. Make use of the answers to problem 1.214. So what was that? There is a uniform sphere of whatever. Find the strength and potential of the gradation field. Right. Of this sphere as a function of the distance r from its center. Right. Something like that, huh? I get it. So you just want the potential energy. Okay. There was a different thing that I could use. So what was that? Oh, okay, maybe we should not be using that. So what I was thinking was, for the second case, because it's a 3D situation, what we could do is just use like half epsilon naught E square. That's the energy, so the potential energy per unit volume, and then this times dV, and then you just integrate this guy, right? So that's a formula that comes in use for, what was that once again, electromagnetic radiation, and we can actually apply it in this case as well. But yeah, let's not go for stuff like that, because first of all, I'm not very familiar with this thing, and secondly, I don't know how to integrate this thing, because E is gonna, yeah, not nice. We'll just do the usual start charging the thing kind of problem, right? Yeah. So they are saying a uniform sphere of mass m and radius r. All right. Uh, Interesting. So how would we think? Right. Like, how would we do that? Huh? You could, okay. So the second one, you could just, right. So first of all, for A, you'll just figure out what is the energy to form a surface, and then using that we can try to do for B, because you want to form a surface as well as you want to bring those particles close to the already formed sphere to increase the sphere's volume, and then keep going, right? Let's do A first. A thin uniform spherical layer. I know they want us to do B, but I won't. I just won't, right? Okay. A thin uniform spherical layer of mass m and radius r. right? So yeah, I mean, just think about it. You got this surface. So this surface is rigid but very light, and on top of that, you are starting to put some mass density, right? Such that, yeah, basically like charging the surface, if that makes sense, talking in terms of electrostatics, right? Yeah, and then in the end, we just have it completely charged or completely filled with mass to some density, right? So uh, let's start putting in mass. At some point, it has mass m. Now, if you want to put more mass on this thing, so dm mass, yeah, what we could do is, bring a blob of dm mass towards it and then just put it right there and then try to separate that mass out. Okay, maybe that's not a good thing. We should try putting, dm mass from here, something like that, right? This is complicated because in this case as well, you are forming the surface of that dm mass. So how can you neglect the interaction energy between the particles of that dm mass? Uh, yeah, that's kind of complicated. How would you do that? Okay, maybe we should just, figure out the interactive energy between all of these. Right, you could use that thing. Okay, I know a way of doing so. Right, get rid of all of this. First of all, we'll do this for completely discrete point masses. So an assembly of point masses. I know there is, right. So this same thing was done for electrodynamics somewhere. I don't remember where it was, but I can do this thing for this guy as well, right? So let's try it out. Uh, yeah, okay. So think about it. You got a mass, and so this mass has a, right. So all of the other masses, they produce a potential V at the place of that mass, right? Oh, this is kind of weird. Maybe that's not the way to think about it. You want the interactive energy, right? So you want this thing, summation of G M I M J upon R, where IJ, right, you get all the interactions, and MI and J, right, it's kind of a set. IJ sets all of them. You get all of them, and then sum them up, you will get this thing. Uh, yeah, right. And I and J both run over the same set, and I and J cannot be equal. So if the summation I is not equal to J, it's kind of like a double summation, if you ask me. All right, and you're summing this up, and I goes from I don't know, 1 to n, and then j also goes from 1 to n, right? That's the kind of sum that we are looking for. So what we can do is, insert this extra stuff. So g, m, I, oh, this is not helping. Okay, something else. Right, okay, let's do it like this. So this thing can be thought, so you can use a table format for this thing. You got values of I in this side and j in this side. So you got 1, 2, 3, so on till n, and then you got 1, 2, 3, so on till n. So this complete diagonal, all the elements on this diagonal, you don't want any of these guys. So you don't want this, you don't want that, so on. But you do want this thing, you want that thing, and so on. So yeah, think about it like this. Stuff that you're doing, isn't that just this whole table? So the sum of all the elements inside this table except the diagonal elements, right? Yeah, so this is just equal to the summation of g m I m j upon r. So now it's the whole table, right? So I, it goes from n to 1, and j goes from n to 1, and then minus the diagonal summation, we just call it as d for now. This whole summation, you can actually split this up. So for each mi, the mj runs, right? But mi doesn't change. So you can factor that out. So this basically just becomes, oh, and by the way, the distance between them. So, oh, oh, this is unexpected. I was not expecting this thing. So the distance between them is different. I was so close to getting the thing, but these R values are different. Oh God. Oh, hey, I could do this thing, So I can just say, and by the way, I and j can be equal in this case as well. So, yeah, okay, let's take GMI common and we'll just sum this thing up. Actually, you know what? No, let's take MI common and we'll sum this thing up. So, MJ upon R, right? Okay, is this making sense? Oh, it is not making sense because you should not have repetitions. So actually, right. So the way you do not have repetitions is that you make this thing happen. So you have this kind of constraint that one is less than or equal to I is less than or equal to J is, sorry, it's not equal to, it's just less than. And this is less than or equal to N, right? You should have this constraint and then you would actually get the true potential energy, not the potential. But in that case, right, you cannot have I being more than J. So all of these cases are just wrong. You cannot have these things. Um, oh, okay. So now how do you get this sum? So call this sum as S, then 2S plus the diagonal sum that is equal to the whole sum. So it's called T for table. And then this whole table sum, I think we can actually do this thing. So it's just equal to this thing. And then you can write it like this. So it's Mi times, so it's actually summation of Mi. Summation over I of Mi, and then it should be in bracket, and then you also got this other summation, so GMJ upon RIJ, right? Yeah. If you think about it, this whole thing is just the potential that I feels because of all of the masses combined, right? So along with I itself. So this actually is just the potential, right? Yeah. So the potential. That makes sense. For I. So all you gotta do is just figure out what this thing is, and then you will have the table like it. So 2s is equal to that, and then that just means s is equal to 1 upon 2 summation of mivi minus, right, 1 upon 2 d. That makes sense. Okay. How do you get the diagonal sum? It's just equal to summation of g mi squared. So summation of, okay, what's happening? G mi squared, right? Because we'll just have these being equal. And then that thing upon, oh God, what is the distance between these? That is not nice. Oh God, this is not nice. How did this, okay, I mean, something didn't go correctly because Ri for that is supposed to be 0. So, so Rij for that is supposed to be 0. And then this would just go to infinity or something like that. Okay, in the original thing, we didn't have this problem. So think. So if you like, okay, you know what? Let's do it like this. So we'll just say 2s is equal to t, where t is not defined as the sum of the whole table, but sum of the table except this diagonal elements, because these diagonal elements are actually going to infinity. So we don't want these guys, right? This thing is equal to s, right? Yeah, and then this will just become equal to summation. So the double summation, of course. And we can just say summation of mi over I, right? And then you got summation of gmj upon rij, as, yeah, j goes from 1 to n, but it doesn't equal to I basically. So except I, it takes all values in it, right? So isn't this thing, so this summation equal to the potential because of all the masses except the ith mass? That makes sense, right? So you can just write this equal to vi. Okay, so what we finally got is, right, we don't need this thing, it's just this. So the energy that we look for, so our potential energy, is just equal to half summation of mivi. Cool. But here's the catch. Vi is the potential because of all particles except the ith particle. So the one for which you are calculating the vi, you don't want that particle to be involved. Does that make sense? Right. Once you have this thing, you can just apply it in the integral form. Right. So you can just say it's equal to the integration of em, and it's over the whole volume or surface or whatever, and you got vi. Or because you got like assembly of negligible masses, right? So all of these mi, those will approach zero. So you could just write v. So v is the potential at the point, not the potential for all the points except mi. Just include that in there as well, right? Doesn't really change anything because that point is of a zero mass basically. So yeah, right. Doesn't matter. You just have this as the thing. Right. This was the formula that right. This was like an intermediate formula that you would get. And of course, we are saying V for potential. We should actually use U or something. Nah, just gonna use V for potential. But whatever. So finally, we have the thing, right? Yeah, we have the thing. Uh, okay, now let's do the thing. So 217th, find the proper potential energy of gravitational interaction of matter for a thin uniform spherical layer of mass m and radius r. Just want to do this thing, half integration of Tm times V. The V is actually constant throughout. It's just equal to Gm, so the total mass of this guy upon the radius, right? Yeah. And then you just want half integration, right? So basically this just becomes Gm squared, because the integration of Dm is that, upon 2r. There we go, that's 8. So even without doing any actual integration or any assembly, right, of these masses, we still found out the thing. So, right, isn't that nice? Gm squared upon 2r, that's what you got. Let's do B now. So I have to keep this formula in the back of my head from now on, because this looks to be surprisingly nice actually. And V is not that hard to figure out. So it's awesome. Okay. And then what do you got? You got a uniform sphere of mass m and radius r. Make use of the answer to problem something, whatever. So you just want the potential of some point inside of the sphere, right? And then you want actually not some point, a whole spherical shell basically. Right. Let's do the thing. So for that shell, what is the potential? It's given by G. The mass is now, okay, no, you don't want it to be like that. What is the potential? So it's Gm upon R going from, so at the surface it's just that thing, but then after that it changes. So the field is now proportional to R, right? So the field is like Gm upon R cubed times R. You want to integrate that thing. So integration of this dot dr or whatever like that. So R squared minus capital R squared, right? And then half of that, of course. So you will get this much more energy when it's sucked in, and then already you got this energy, or energy upon mass, whatever, and then you just add them up. That's the potential, hopefully. And of course, all the potential energies that we're calculating are supposed to be negative of what I'm showing, but whatever. So this is just going to be Gm upon R, and then you got 1 plus 1 upon 2, and then you got R squared upon R squared, so 2R squared, and minus 1 upon, hey, that R is already out, so it's just, okay, that is out. Yeah, it's got 1 upon 2 plus this guy, right? So Gm upon 2R, and then you just got 1 plus R squared upon capital R squared. Yeah, that should be the thing. Okay, so you got this. Perfect. So instead of V, we can just put this guy. And for Dm, so you got a spherical shell, right? So the density, okay, let's not do it that way. Just find the volume of the spherical shell. What is the volume? It's just 4 pi r square dr, and then divide by the total volume, which is just 4/3 pi r cubed, capital R cubed, by the way, right? So this cancels, just get 3r squared upon capital R cubed dr, whatever, something like that. So this thing times the mass. That is what dm is. Just gonna put that over there. Where did that go? Okay. Just multiply and put there. Cool. So when you multiply, what you get? Just get gm squared upon 2r power 4, I think. This thing is already just 3r squared, so okay, hopefully something nice will happen. Got 3 outside, we got r squared times 1 plus r squared upon capital R squared. Okay, and then you got dr. Sure. You know what? I'm thinking of something different. I can write it like this thing. And then, right, let that be r, and then you got this. So r upon r, make that another variable, right? So then you're just integrating this from r is equal to 0 to capital R, but then r upon r actually goes from 0 to 1. So this is just integration. So you can take that out. 3gm square upon 2r, that's out, and then just integration from 0 to 1 of x square times 1 plus x square and that times of dx. Hopefully this will turn out to be correct. I have really no hope at all for this thing, but let's see what happens. I did it correctly or not? I guess I did. That is the r cube, that's just r cube. So perfect, our dm value is correct, v value looks to be correct, so yeah. So for example, at r is equal to, oh, it doesn't, wait, what? At small r equal to 0, this should not be gm upon 2r, it should be, no, it's not gm upon 2r, it should be 3gm upon 2r, not this. Oh, I messed up something. Huh. Right, where did I mess up? Uh, oh, come on, seriously. Okay, once again, figure out the potential now correctly this time. So Gm upon R initially, and then you just got, right, other stuff. So come on, think what's the what's the field? It's just yeah, this thing, right? You want to integrate this thing with this, right? So this dot dr, and then integrate that things like you got Gm upon 2r cubed, and this is going from the surface to some point in between. So just got r squared minus capital R squared, right? Hopefully, which is just equal to gm r squared upon 2r cubed minus gm upon 2r. So when you add these up, something doesn't feel correct. It should drop down when, oh, it should be this thing. It should be capital R squared minus small r squared, because it's supposed to be a positive quantity that we are doing, right? And then you actually have that. So it's negative of this thing and positive of that thing. And when you actually combine, you just get 3 upon 2 gm upon r, and then minus r. That's how it was supposed to be. So you got this stuff, gm upon 2r, and then 3 upon 2 minus, actually that is 3 because not, that 2 is just out, right? So 3 minus r squared upon capital R squared, right? So it's not this thing, it's supposed to be that, right? So where did that question go? Okay, first of all, make that correct. It's just this. And now, after doing all of this, you can put that in there and just get 3 minus x squared. And that will give us the correct thing. Hopefully. Uh, right. Did I make any more mistakes? You got the potential correctly this time. So, right. And then dm value also, yes, it's correct. The formula is correct. I think it is because this was correct. So, yeah. Just have to integrate this thing and then we'll be done. Right, exactly. So you got 3gm squared upon 2r, the integration of that thing. So first of all, you got 3x squared. So yeah, dx cubed basically. So that's just 1 minus x power 4. So x power 5 upon 5, 1 power 5 upon 5. That 0 part doesn't count. So this is the thing. It's just going to be 4/5 like this. And then Yeah. This will be 6 upon 5 gm square, or this thing upon r, of course. So 6 upon 5 gm square upon r. Hopefully this is correct. Is it correct? I still doubt whether or not this is actually correct. That's what we got. How can we get something different? Let's do something wrong. No, it should be. Just move on. I don't know whether or not this is correct, but let's just move on. Right? Maybe I should have done that question 1.214 because I would have got that other formula after doing this, right? So what was that other formula? It's, on a side note, the energy is self energy is going by this thing, all right? Or just energy E. Does that even matter? So the energy E is given by this thing, and also the potential at R, that is given by Gm upon 2R times 3 minus R squared upon capital R squared. Cool. Those two formulas we have to remember. Next, you got 218. Uh, Two Earth satellites move in a common plane along circular orbits. The orbital radius of one satellite is this thing, while that of the other is this much less. So two different radii, two orbits. Okay, two Earth satellites move in common plane. Okay, understandable. What time interval separates the periodic approaches of these satellites to each other over the minimum distance? What? Periodic approaches of the satellites to each other. Okay, over the minimum distance. Ah, right, fine. So when they have a minimum distance, those points, what time interval separates those points? Those points in time, that is. Right, okay. So you just need the relative angular velocity. I know that's a weird concept, but the relative angular velocity, just find that out and you will get the thing. Oh, and also you need the time periods. Um, no, just think the relative angular velocity is what we need. Yeah, once you know the relative angular velocity, you are good to go. So once again, just go to our formula sheet that I just made before even doing anything. Right, so you got a time period as this thing. So t is just proportional to a power 3 upon 2, right? Time period is proportional to a power 3 upon 2. Wait, you want the time, oh god, you don't want proportionalities, you just want the actual stuff. So you will actually have to put in the thing. So what was it? It was 2 pi upon square root of gm, and then a power 3 upon 2, right? That's time period. So from that you can just say omega is equal to square root of gm upon a power. You know what? I think this is a much better thing to remember instead of, because this 2 pi, it's like it was naturally over there, right? Yeah. So there we go. You got the angular velocity. Now you would just need those two guys' angular velocities. So the relative angular velocity, which we'll just call omega relative, that's just equal to how much? It's equal to square root of gm times 1 upon a1, or just say r1. R1 power 3 upon 2 minus 1 upon R2 power 3 upon 2. So now you just want 2 pi upon this thing and you get the thing, right? So 2 pi upon square root of gm and then 1 upon all of this. Uh, yeah, how do we do that? How do we do that? Uh, any ideas? Oh god, it's not nice. So the Earth's radius is 6,400 kilometers. This thing is something like 2 hour whatever. And this is 70 kilometers less. Okay, so this thing R1, right? It's like this thing minus 70 and then plus, okay, that's gonna be R1. This is gonna be 6400 plus this guy. And that's in kilometers. Oh god, not nice. Hmm, what can we do? What can we do? What time interval separates the periodic approach? Hey, you could just use binomial theorem and get like approximated, right? Yeah, you could. So what if R1 and R2 are very similar? So in this case, what's happening is that R2 is something more than R1, right? Or R1 is something more than R1. So R1 is something less actually. Does that even matter? So it's just R naught minus del R. And R naught is this thing. So R naught is 7. No, it's 7,000 plus 6,400 kilometers, right? So R naught is what's this, like 134 times 10 power 5 meters. And delta R is just 7 times 10 power 4 meters. So this income, like basically 0 0.7 versus 134. Which of them is smaller? I mean, much smaller. Of course, 0 0.7, right? It's much smaller than 134. So what was I saying? Not that which one of them. So I was making the point that delta R is much smaller than R naught, right? And using that, you can use the binomial theorem. Sorry, the general binomial theorem, that approximation. Just do it. So this thing just becomes square root of gm upon r naught power 3 upon 2. And then, yeah, once that's out, you can write this thing as 1 minus delta r upon r naught, because that, yeah, okay. And that is power negative 3 upon 2. And that thing minus 1. So doing the whole stuff, you just get 3 upon 2 delta r upon r naught, right? Yeah. So this will just become 3 upon 2 delta r upon r naught. So 3 square root of gm times delta r upon 2 r naught power 5 upon 2 or something. There we go. That's our value, right? That's the time required. Yeah, I mean, this is actually a nice formula. I should actually remember. And you know what? Let's just put that in our formula list, because, yeah, go up. So this is one formula, this is another formula, this is another formula. Okay, let's move on. Oh, and once again, you need what these quantities are. So, perfect. Yeah, this should give us a thing. Okay, what I'm thinking is, so GM upon capital R squared, you do need that thing as well, because to get the gravitation acceleration, right? Simplify it a bit. Nah, just leave it like that. Do we actually have to simplify? You know what? No, we do have to simplify it, because if we can't find the answer, why stop? So this will be square root of g upon square root of g basically, which is, yeah, just square root of g. Just keep it like that. Hey, wasn't this like having 2 pi over the, it was. Uh, this is omega, not, this is omega. It is not your, what do you call it? The time required. No, the time required would actually be, so t would be 4 pi r naught power 5 upon 2 upon 3 square root of gm times delta r, right? This is what t would be. So this is wrong, and this is the actual value, hopefully. Let's do the thing. So the time required is, and I would say it's, well, let's not jump to conclusions. We'll first of all figure it out, because, yeah, I mean, delta is a very small value. So, okay, I'm starting to think that maybe it was wrong to approximate, because unfortunately, when you approximate, things go wrong. What if we run into problematic error over there? Because you are dividing by something that is very small. So this will turn out to be very big. But then the bigger it is, the more the error becomes. So, oh God. This is the approximation. But what other choice do we have? Given the exact values, you will never be able to calculate that thing. Just do the thing. So you got 4 pi r naught power 5 upon 2, which is whatever this thing is. We'll keep that for later. Then upon 3, this thing can be thought of as, so square root of gm is square root of g times square root of small g times the radius of earth, delta r, right? So square root of g is approximately pi, the engineer's like theorem, whatever. It's not a theorem, just an approximation. And then you got this thing. For r naught is, where did that go? This, right? So this is, wait, why is this 5/3? It's supposed to be 5.2. You can see that over there. So, wow, this is draining. You're gonna get a square root, and that's just bad. I don't want a square root. You will get a square root. Why am I getting a square root? It should give us the, right, it should be in a time, not, oh no. This doesn't have a square root, this has a square root. It's gonna have meter to the power of 1 upon 2. This is dimensionally incorrect. Oh god. What went wrong? Why is this not working? Okay, just leave it like that, because first of all, this is wrong in any case, because we did a very bad approximation on this thing. And yeah, it's just wrong basically. Sure. We got the omega stuff. It's a power 3 upon 2. But in that case as well, like you would have square root of, oh, okay, it's not wrong. When I made this go away, square root of g contained units as well. Why did I cancel those? That should not be correct. I should not cancel the units of g, just cancel the value. So then it's not wrong. After this part, no dimensional analysis, because you cancel some units over there. So 4 upon 3, r naught is just this stuff. So 135 times 10 power 134, doesn't matter, but whatever. Power of 5 upon 2 upon capital R, which is right, it's just 64 times 10 power 5. And then you got delta R, which is 7 times 10 power 4. Hopefully this will give us something nice. And yeah, okay. 134. The 2 times of that is like 128. 128 versus 134. Close, but not close enough to cancel it directly. Yeah, don't do that. I want to cancel this though. Who cares? We just want an approximation. I mean, our guess will be wrong in any case, so might as well approximate it to the end, right? So you got 21 over there, and that's going to be just 2, so 8. Now, one of these degrees is gone, but 10 power 4. You can make one of these go up to 134 times 10 power 5, and finally just got the square root of this guy, square root of 134 times 10 power 5. Okay. Right. This cancel, just get 10 over there. 21. 4, no. 21 doesn't match. What was 7? 7 match 7, 64. No, it doesn't. Well, 763 is close enough. So approximate, or you could just write this as 20 and 135. No, that's just wrong. You don't do it like that. It's 8 times. So yeah, divide like by 7. So you got 1, 64, approximately 69. Sorry, approximately 63, which is 19, or okay, that's very close to 20. I should have done that already. Just approximate it. 8 times 135, so that's like 4 times 270. So 4 times 270 upon 20, this cancels, you get 54, right? Times 10 times square root of all of this. So take the 10 power 4 out, it's 10 square, and then square root of 1340, right? So 102, okay, no. 2 power 10, that's like 32. 32 square is this thing. 33 square is like 9 times 121. This is just the 981. Carry on, about 1089. Not close. What else? Yeah, just keep on going. Where was I? I was like 32, 33, 34. Check 35. 35 square, what's that going to be? 35 times 35. You got 5 to carry on 15, it's got 7. So 0 and then 5 and carry on 9, 1, 0, whatever. So 1, 1, 1, 2, 1, 5. Still not close enough. 36. This is taking forever. 36 squared. Perfect. Right? 36. So 6 times 6 is 36. 3 carried on. What's this? 18. 18 times 3, 21. Then 0, 3 times of that. So 8, 1 carried on 9. So 1, 0, something. Yeah, that's usually close. So 1, 2, 9. I'm guessing that 37 is where you will get over this thing. Let's check that out. So 37, 37. It's got 9, 4 carried on, 21, 4 is just 2, 5. Then you got 0, 1, 2 carried on, 9. And then, what am I doing? Sorry. Yeah, 9 into just 1, 1, which is 1, 3, 6, 9. Actually, which of them is, yeah, this is actually much better. Let's just say this thing because, no, we actually made this slightly bigger than what it should have been, right? So let's make this slightly smaller than what it should be. So let's make this equal to 36 instead. So this thing will just be 36. All right, let's finally calculate this out. So you got what, 54 and then 36. So 4 to carry on, but 3, 0, 2, 1 carry on, 15. 4, 4, 9. So 1944, approximately 2000. Okay, let's not jump to that conclusion. So it's 1944 times 10 power 3, right? Uh, approximately 2000, right? So 2 times 10 power 6. That's how much it would be approximately. Good, right? Next question. These many what? Seconds. What do we want it in? These many seconds, of course, because SI units. So yeah, divide this thing by something's wrong because okay, 10 power 6, huh? So divide this thing by, oh, if we actually had to do that, why? Right. So you got 3600 seconds. That's like 1 hour. So these many hours. Then divide this thing by 24. These many days. That's the thing. So it takes multiple days for it to get back. Huh. Interesting. So this is what's this, 9 times 6 or whatever. So multiple of 6, 90 multiple of 6. 90 upon 4, which is 45.2, which is 2.5. So it's 22.5 days. Remember, this thing is days. It takes around 22 days or 20 days because our approximation is very bad. So around 20 days for it to reach. Oh, okay. This was to be expected because the angular velocities of both of these guys is very close. So yeah, that's our answer, 20 days. So around 20 days. Hopefully this is correct. Let's go to 219. 219 is calculate the ratios of the following accelerations. The acceleration W1 due to the gravitational force on the Earth's surface, the acceleration W due to the centripetal force of inertia of Earth's equator on the Earth's equator, and the acceleration caused by Sun. Wait, sorry, what? So W1 is due to gravitational force on the Earth's surface. Fine. Then W2 is due to the centrifugal force caused by force of inertia on the Earth's equator, right? But why do you want me to calculate this thing? An acceleration W caused by the sun to the bodies on Earth. Does that make sense? What? Ws is the acceleration caused by the sun to the bodies on Earth. Isn't that just the acceleration of the Earth? Because with respect to Earth, both have almost the same acceleration, right? So with respect to Earth, that acceleration is just 0. And with respect to Sun, this acceleration is the acceleration of Earth. So, what is this? I don't understand. In what frame do you want this acceleration? And then this is the acceleration centripetal, centripetal force of inertia on the Earth's equator. Ah, that's it. I'm not doing this. 219, just leave it be 220 because this is just a lot of calculation, and moreover, it depends on actual data. I don't have that, right? I mean, okay, I might have Earth's radius, the length of a day, something like that, but the radius between the sun and Earth, no, I don't have that. The centripetal acceleration of Earth, how do you figure that out? Okay, maybe using the mass of the Earth or something like that. So m omega square r, you still need r for that, don't you? Oh, that's like m. Okay, just omega square r. Yeah, you know what omega is, but you still need r for that to actually work. And we don't know what r is, so yeah, just 220. Next question. At what height over the Earth's pole the free fall acceleration decreases by 1%, and what is it, semicolon, by half? Oh, so two questions. First by 1% and next by half. So height over Earth's pole, the free fall acceleration decreases by 1% first, and then it decreases by half. So that acceleration is pretty much just gm upon r squared, which is m upon r squared. So it's inversely proportional to 1 upon r squared, right? And we want just height. So just say r plus h squared, whatever. This thing using the binomial theorem can be thought of as gm upon r squared times 1 minus, so yeah, like 1 minus 2 h upon r. So you want this to decrease by 1%. So the first case is very simple because you just use binomial theorem and get the thing done. This thing, yeah, like, okay, this thing is corresponding to 2%. Basically, h upon r is corresponding to 1 upon 100. So, oh, it's capital R actually. Doesn't matter. So h is just the radius of Earth upon 100, which is 64 kilometers. That much should be your height. So the first thing I just got the thing. It's 2%, right? Not 1%. Where'd that go? No, it's 1%. Okay, this is corresponding to 1%. So right, h upon r is corresponding to 1 upon 200. Yeah, this thing upon 32 kilometers. Fine. So A is done. 1% stuff. Its h is equal to 32 kilometers, around 32 kilometers, because it's an approximation. Okay. Next, we also want, when does this become half? So this thing should just be 1 upon 2 of g upon r squared, right? So just got this thing, r plus h is equal to square root 2r. So h is just equal to square root 2 minus 1 upon nothing. Okay, square root minus 1 r, right? There we go. It's like 0.4142 times the radius of Earth, which is 6,400 kilometers. And we want everything in kilometers or what? It's just taking forever. Uh, okay. So how much is this? Just do it in kilometers. So it's like 41.42 times 64 kilometer. And this is an exact value, so we'll keep it exact, right? Except that this is actually not exact, but whatever. Yeah, just calculate this thing. 414264 5 6 16 0 2 1 carried on 5 2 carried on 8. And then you got 24, right? So 6 times 4 is 24. 8 8 0 1 carried on 7 5 now it's 6. And then you got how many, right? So 2650.88 kilometers. Let's round it off. So it's basically 2650 kilometers, right? Yeah, that should be good. Actually 2651, you know. So there we go. 1 upon 2, h is equal to 2650, sorry, 51 kilometers. Next question. 221. Okay, on the, oh, sorry. Yeah, I mean, this also talks about Earth's pole. Okay, pole of Earth, a body is imparted velocity being not directed vertically up, knowing the radius of Earth and free fall acceleration on its surface. Find the height to which the body will ascend. Okay, The air drag is really, yeah, I mean, that's a very big problem because it actually is not negligible, but well, whatever. Knowing the radius of Earth and free fall acceleration on the surface, find unless you're actually going at very high speed, so you exit the atmosphere very suddenly, right? But okay, at that high speed, you might as well just escape. So what's the deal? Anyway, on a pole of Earth, a body's imparted velocity will not upward, so it's gonna go up, then it's gonna come down, whatever, right? So till what height does it go? At that particular height, its velocity is zero, so it's got gm. And should we approximate? No, that's not. Gm times 1 upon whatever height it approaches. Initially, it was just the radius of Earth, then minus 1 upon r plus h. This is just equal to, what was it once again? Uh, yeah, half v squared was. So v naught square upon. Cool. And we know what small g is. So small g is just gm upon r squared, whatever. So we can write this thing as small g and then r squared. So 10 times r and 1 minus r upon, or you could just write this. Yeah, 1 plus h upon r power negative. I don't want to do this thing, but it's like telling me to do this. How can I not do it in that case? Right? Ah, wait, but if you just approximate, you will get mgh is equal to, no, that's not right. That's the usual kinematics. That's not what we want to do. You want to figure out what h is in the proper way, right? And not using approximations. That is wrong. Don't do it like that. So it's this thing, 1 minus 1 r upon r plus h. Let's figure out h through this equation. So 1 minus r upon r plus h is just equal to v naught squared upon 2g. And what is given to us, by the way? Radius of Earth is given? Perfect. So 1 minus v naught squared upon 2gr, that's just equal to r upon r plus h, right? This is basically just equal to 2gr upon 2gr minus v naught square is equal to 1 plus h upon r. So h upon r is just this thing minus 1, which is v naught squared upon 2gr minus v naught squared. Perfect. So h is just r v naught squared upon 2gr minus v naught squared. That's gonna work out. Cool. Yeah, just submit as an answer. So it's just r v naught squared upon 2gr minus v naught squared. Next question. If I had approximated this thing, I just got like 2gr is equal to v naught. Right, that I would have got that, which is not correct. Okay. So 222. An artificial satellite is launched into the circular orbit around the Earth with velocity something related to the reference frame moving translationally and fixed to the Earth's rotational axis. Reference frame moving translationally. What? Oh, okay, like that. Find a distance from the satellite to the Earth's surface. What? But, this is weird. Must be relative to the reference frame. Radius of Earth and free fall acceleration on its surface are supposed to be known. Right, but what about it? An artificial satellite is launched into a circular orbit around the Earth with velocity something related to the reference frame, moving translationally and fixed to the Earth's rotational axis. So you got this Earth, you got the rotation axis, this reference frame. It is like, yeah, so the rotating reference frame of the Earth, right? This vector is like rotating, whatever. This is fixed. And what else are we doing? You got an artificial satellite launched into the circular orbit around the Earth with velocity v with respect to this space reference frame, basically. Find a distance from the. Oh, okay. The thing is, okay, what they're saying is that it's in a constant orbit, right? Its orbit is Right, okay, that's actually, it's circular and it remains in that orbit with velocity v. Just figure out what the radius is. Yeah, it's not a big deal. So just v is equal to square root of gm upon r. Uh, that's the thing. You want to figure out what r is, then you get the thing. So r is just equal to v square upon, yeah, gm upon v square. Sorry. So gm, that's just equal to small g times r squared. So this is the thing. There we go. Small g r squared upon v. They didn't give us any values. We'll just keep it like that. Next, 223. Calculate the radius of circular orbit of a stationary, stationary Earth satellite which remains motionless with respect to its surface. Oh, okay. What are its velocity and acceleration in the inertial reference frame fixed at a given moment to the center of the Earth? The given moment, center of Earth. Inertial reference. Oh, of course. If it's the inertial, it cannot be the rotating reference frame. Can it be? Nope. Okay, so there should not be any pseudo forces. That's why. Right. So radius of circular orbit of stationary Earth satellite remains motionless with respect to its surface. Perfect. It's a geostationary satellite. What are its velocity and acceleration in the inertial reference frame fixed at a given moment to the center of Earth? Its velocity is the same thing as the Earth's surface. So you can find that out, right? It just, yeah, r times omega. So omega we know it's just 2 pi upon a day. Yeah, that's weird. Okay, 2 pi upon a day. And that times the radius of Earth. It's doable in the end. So you can figure out what that speed is. Cool. And what else do you want? You want the acceleration. So, right, it just has its acceleration just omega square r, of course. So omega we know square of that is r. Cool. This should work out. No big deal, right? Okay. So, wow, we actually have to figure out what omega is. Omega is 2 pi upon a day, which is 2 pi upon 24 hours, which is like 2 pi upon 24 times 3600 seconds. Just looking at this number is bad. It's just equal to pi upon 12 times 3600 seconds, right? Okay, that's awesome. Uh, what is this? Like 720 and 360, okay. It's like 756, okay. Pi upon 756. Oh, sorry. 3 6 is before, and then you got 7 2. So 436 because, sorry, 2 because, okay, 7 2. So 2 times of that, that's why this thing, and then 0 and then 36. Why am I doing this? So 432 double 0. There we go. This is omega. We don't have a, why did this happen? We don't have a value for this yet. I mean, the numerical value. Okay, what do we want? The first, where did that question go? 223, right? So the velocity is just omega r, which is, okay, let's do the thing. So you got pi 432 64 and all of this times kilometer per second. It's 32, not this thing. And it's kilometer per second, I guess, because this is a second inverse hertz, right? Okay, amazing. 432. Maybe something is related to 3.14, something like that. 3.14 and then but 432 doesn't look very doable. 314 versus 432. Any common factors for this thing? Well, 2 is a factor, so it's like 157 upon 216. Any more common factors? 3 is not a factor for this guy. 7, don't count on that. 11, no, nothing. And just approximate or something. So you can write 150 upon 200 or something like that, right? Yeah, don't do that, right? Just leave it like that. So you got Do we really have to? No, that's just unnecessary torture. I don't have the time to do that. Okay, and the acceleration is just omega square r. That's it. Won't give you anything else. Just move on. And omega is of course this thing. Now calculate it on your own. And r is just 64 times 10 power 5. Cool. Next question. That's it. Not gonna do anything. 224. Satellite revolving in a circular equatorial orbit of radius something from west to east appears over. Oh god, I hate these directions and whatnot. So how is the earth okay, according to earth the sun goes from east to west, right? So uh, the earth is rotating from west to east. So if there is a direction which we call as west and the direction east, then it's going from west to east, right? Okay, what you are saying is a satellite revolving in the circular equatorial orbit of radius whatever is going from west to east. So this is also rotating in the same direction as the earth. It appears over a certain point at the equator every, we know west is like in that direction, whatever. Okay, appears over a certain point at the equator and over the equator, the orbit. Perfect. Every 1 point, so 11.6 hours. Okay, its radius is given. Uh-huh. Calculate the mass. What? Why is that the gravitational constant is supposed to be known and the radius of earth that is not supposed, oh god. In using this data calculate the mass of the earth. Why? How is that a way of calculating the mass? I don't get that. Whatever. So uh sorry, once again, what should I do now? A satellite revolves in a circular equatorial orbit of radius something from west to east, appears over a certain point. So with respect to this guy, its angular velocity such that it appears in time period equal to 11.6 hours. Fine. So 2 pi upon that. Okay, doable. And what is the thing? Its radius is given, so you can figure out the angular velocity. Yeah, that's the way. So once again, what was the angular velocity? We actually got a formula for that now. Square root of gm upon a power 3 upon 2. In this case, square root of gm upon r power 3 upon 2. They already gave us what r is, right? Okay, let's choose capital R because that's what they are using. And everywhere, I'll just choose r of earth, right? Okay, so this is the angular velocity for that guy. Now this thing minus the angular velocity of the earth, which is omega earth r earth. Oh, sorry, not r earth, just omega earth. Yeah, and that is equal to 2 pi upon the time that they gave us. So this thing, right? Yeah. Using that, you can figure out what this thing. And also the gravitational constant is supposed to be, oh, so this thing, that's known. And using that, you can figure out what m is. Yes, but why? Why do you want to do it like this? So it's angular velocity of earth plus 2 pi upon the time. Okay. This times r power 3 upon 2. You just want the square of that, so like r cubed actually, and all of this squared actually, yes, that's equal to gm. So this thing upon g, this is the thing. And no, I won't calculate it. You can if you want. Why is this happening? Okay, and tell me how accurate it actually is. 25. Satellite revolves. Why does it look like I'm doing this for some kind of department that actually needs these values? I don't know. These don't look like the usual textbook questions. Okay, satellite revolves from east to west. Once again, the direction. Why are you doing this to me? So Earth is from west to east. It's on. Yeah, this is from east to west. So it's in the opposite direction. Fine. Yes, in a circular equatorial orbit of radius r equal to this thing, around the Earth. Find the velocity and acceleration of the central line in the reference frame fixed to Earth. I'm gonna kill somebody like that. So you just want the omega relative, and using that you can get the thing. So omega relative square r, that's what acceleration. Omega relative times r, that is the velocity. No big deal. And omega relative, how do you figure that out? So the actual omega for this guy plus the you don't want to be doing like that. You're right. We know that it's supposed to be omega relative. I know it, but it doesn't feel correct. Like, how do you figure out omega? Okay, you actually have to figure out omega first, and then you can do this thing. What was omega once again? Using this stuff, yeah, square root of, now I just know the value. Square root of gm upon r power 3.2. Right, finally, now I have this memorized. Okay, plus omega e, that's the omega relative. So there we go. This times r, and this times the square of that times r. Alright, this should work out. So this is the velocity with respect to uh, Earth, and then the acceleration with respect to Earth, that's just equal to distance squared. So remember, r dot is just 0, so no big deal about that. And then you got plus omega e, this stuff square, and r, and yeah, I'll just leave it like that. I won't calculate. So 226. Let's go. Satellite must move in the equatorial plane of Earth close to its surface, either in the Earth's rotation direction or against it. Find how many times the kinetic energy of a satellite in the latter case exceeds that in the former case. In the equatorial plane of the Earth, close to its surface, either in the Earth's rotation direction or against it. Okay. Find how many times the kinetic energy of the satellite in the latter case. So when it's against it, um, exceeds that in the former. Oh, okay. In the reference frame fixed to the Earth. Oh, okay, cool. So yeah, right. It's just like square of v or something like that, right? So half mv square because it's close to the Earth. So yeah, we got what this, and for that case, it would just be negative of this thing, square of that, right? So yeah, it's just this thing, square root of gm upon r cubed. This is very weird. Plus omega e upon square root of gm upon r cubed minus omega e, all of that to the power of, yeah, what was that once again? 2. There we go. That should be the thing. So this is the answer. Next, 27. Okay. An artificial satellite of the moon revolves in a circular orbit whose radius exceeds the radius of moon this much times. In the process of motion, the satellite experiences a slight resistance due to cosmic dust. Assuming that the resistance force, okay, it depends on the velocity of satellite as f is equal to ab square. Okay, where alpha is a constant. Find how long the satellite will stay in the orbit until it falls over to moon's surface. Okay, cool. So the, oh, once again, it's that kind of question. This is bad, but you have to do it, right? So if the satellite's radius vector is given by r vector as a complex number, by the way, all right, this guy's force on this, okay, that's given. So there's this force and that force. It's in two different directions. You got this acceleration, it's just gm upon r squared, and then you got a tangential acceleration on this guy. So let's not even use the complex numbers for this thing, because, or maybe we should. And what's the thing? How long before it falls to the moon's surface? Interesting. Well, whatever. Just got AB square, right? We'll see what happens. And the only tangential force is, of course, this much. Yeah, this is completely tangential. Wait, it's, oh, it's not like, okay, it's not tangential. It's just, yeah, it just opposite to the velocity. Uh, Not nice, not nice. The problem with this thing is, what if its velocity is not in the direction normal to a radius vector? Then yeah, you will not have that thing happening. So you have to go for the complex number. Oh god, I don't like it. Well, whatever. So the d square r vector upon dt vector stuff, right? What is that equal to? Right. Okay. We'll do it. No big deal. We can do it. Yeah, that's stupid. So you got acceleration in this direction. It's just this much. So it's gm upon r square negative r hat. Okay, and let's just say alpha upon m. That's beta. So we'll define alpha upon m to be beta. This is beta v square, right? And this is going to be in opposite to v, of course. So negative beta v square v hat. Okay, interesting. This is just 2D motion. That's perfect, right? It's just 2D motion. Okay, don't rush this. Might not be correct to do that. Come on, think about it. And what do you want? How long before the satellite falls down? Hmm. It's a weird equation. So you got the acceleration plus, so beta v times. Why is this like so weird? Beta v square, and then you got v hat plus gm upon r square times r hat. This is equal to 0. That's the differential equation. And now somehow you have to figure out how this works. I hate this. Come on. How do I do this thing? You could write this as like v times v vector. Sure. I don't like the way it feels. We will have to solve this differential equation. But how? How do I solve this? A slight resistance. No, I don't know. I just don't know how to solve this thing. There has to be a way. But I've never seen something like this because it's v squared. You have that as the thing. This differential equation, seriously. Even if I, break it up into pieces, it's not going to work. It's not going to work. Because we don't know where v hat is. I mean, okay, we actually do know, but that's a very horrible thing to figure out, right? Oh, come on. You could write in different forms. Oh, it's not helping. Uh, Come on, think about it. We can just give up on this small v vector upon v. That's how I can do it. There's another way because I mean, how else am I going to do it? I either have to do this thing or this thing. I guess this one is better. Something. Why is this dependent on v and not r? Right? Why is it like that? Why is it dependent on v and not r? V times v vector. And this resistance is like very small, you are seeing? Okay. I mean, we could say, okay, if it's very small, it's always going to change its trajectory to get into circular orbit. Nah, that's just not right. We know it's gonna go into an elliptical orbit as this, yeah, changes its velocity, but its position doesn't change. So it goes into an elliptical orbit. We know that. It can just stay in this kind of spiraling down motion. Okay, I think we should stop now because this is something I can do right now. Okay, how long before it falls down? Hmm. How long before it falls down? What happens when it falls down? Its R approaches, right? It its R just basically becomes capital R. That's like asking how long before its R becomes a certain value, right? That's not right. That's not right. You can't do it like that. It's not helpful. You will actually have to get the equation of R in terms of time to actually solve that. Not worth it. Okay, fine. So I'll see if there is a solution for this thing anywhere. If there is, tell you. So, oh, I wish there was some time derivative hidden over there I could just, use to get this thing done. I can't. Fine. I'll see you guys in the next video. Bye.